So this is the kind of point we got up to last time. Where we introduced the definition of the partial derivative of a function of two variables. So we have a function of two variables f here. F depends on two variables, its first variable and its second variable. Traditionally we'll name them x and y. And the partial derivative of f with respect to y, there's two of these. You can take the partial derivative with respect to x and the partial derivative with respect to y. The partial derivative with respect to y shown here is the limit of this quantity here. So this is evaluated at a base point xy. So you think of the two values x and y as being fixed at some location. And this is very similar to the one variable derivative. We're taking the ratio of changes, so the change in absolute value, the change in actual value of the function, so f evaluated at this nearby point, same x coordinate, but a slightly different y coordinate, y plus a little bit delta y. The difference between that and the value f had at the base point xy, but all this is expressed relative to the size of the difference in the y variable, so relative to the delta y. We're taking the limit of that quantity as delta y approaches 0. And this example we worked through last time, took as an example this function f of xy, which is x squared times y, and we worked out the partial derivative with respect to x, and we found it to be 2 times xy. Okay? The way we did it was we just applied the definition, substituted in the definition of the function f, the first variable squared multiplied by the second one. The x squared y's cancel when you expand that out. You get this kind of expression here. You're taking the limit as delta x goes to 0. There's delta x is above the line and below the line. So you cancel those out to simplify the expression. And then you find it's 2x plus delta x all multiplied by y. And that is well behaved as delta x goes to 0. This bit is just going to disappear, converge to 0, and we'll be left with the 2x times y. You can do the very same kind of calculation, but with respect to the y variable, and this time you'll find that the partial derivative is x squared. So that's a couple of examples of working out partial derivatives from first principles, or just straight from the limit definition. Of course, we don't always, we pretty soon now we're going to stop making explicit reference to the definition, and we're just going to derive our partial derivatives using very similar principles that we have from one variable calculus, together with just this basic principle of partial differentiation, okay, which is given here in bold, this bold paragraph here. This is what we're going to use all the time. So when we differentiate a multivariable function f, say, with respect to a variable x, we're going to make use of everything we know from single variable calculus with just this one adaptation. We treat the other variables appearing in the definition of f, we treat all those other variables as if they were fixed constants, just for the purposes of working out the partial derivative with respect to x. Treat every other variable as if it's a fixed constant, and then just apply the very same principles to f that we have from the one variable case. Because if temporarily we're assuming that all the other variables involved in the definition of f are fixed constants, then really f is just a function of this one variable x that we're focusing on. If temporarily we're treating all the others as if they're just fixed numbers. Really there's only one variable surviving, function of a single variable, and we just apply the same techniques from single variable calculus to that. So we got a few examples of this here, which we can work through. We'll probably do these on the overhead. Let's capture the screen. some examples of this now. For example 1.2, so we're going to take this function, which is defined in the notes, f of xy, and this is x squared y cubed tan 2x. Okay, this is a compound function, if you like, built up out of polynomial terms and a trigonometric function. But we're going to take its partial derivative with respect to x. And we're going to apply this principle. Now, while we're taking the partial derivative with respect to x, we're treating any other variables, okay, there's only one here, y, but we're temporarily treating y as if it were a fixed constant. So this y cubed here, just imagine that that's 2 or something, just some fixed constant. Then what's remaining is a function of a single variable x. X squared times 2, if you like, times some constant, times the tangent of 2 times x. And then we just apply our normal standard principles of differentiation from single variable calculus to this. Okay? So what do we have to do? Well, here we recognize that it's actually a product of two different functions of x. So we have to employ the product rule. So we're going to hold the tangent the same. So we have a term which is be 2 times x times y cubed times the tangent of 2x. That comes from differentiating the x squared part, keeping the other function of x the same. And then you add on to that x squared y cubed, and this time we're differentiating the tan of 2x. And we can make use of a standard result that the derivative of tan is sec squared, 1 over cosine squared. dz of tan z is sec z squared. We can make use of that result. So we're going to have sec squared of 2 times x. But of course, we need to employ the chain rule as well here, because we're differentiating the tangent of 2x. So it's going to be sec squared of 2x, but multiplied by the derivative of the inner function of x. And that's a non-trivial inner function of x there. So we need to multiply it by the derivative of it, and the derivative of 2x is 2. So we get an extra factor of 2 out there in front. So you see, I was using all the various results from one variable calculus there to find that partial derivative, together with this basic principle of treating the other variable y as if it were a constant. If you did have a constant here, multiplying x squared tan x, that same constant would appear here, and also here. So let's look at the y derivative. The f dy. Okay, this time we're differentiating with respect to y. So the other variable, the x variable, gets treated as if it were a constant. And then the complications behind x squared and tan 2x disappear, because we're assuming x is just some constant. So constant squared, tangent of 2 times a constant, it's just some number. The structure of f simplifies to just a constant times y cubed. And we have to differentiate that with respect to y. It's going to be that same constant times 3y squared. Okay, so we get 3x squared times y squared times the tangent of 2x. So these are the two partial derivatives. I'll put in this phrase here, first order, and we'll see what that means in a moment. They're the two first order, or just the two partial derivatives of f. Any questions about just what we were illustrating there? We'll get plenty of practice at that today. I've got an extra example problems sheet here which I'm going to hand out in this lecture, and we'll use this as the focus for this evening's session. So I'll take the second lecture this evening. Was it 5 or 6? Yeah. So we'll make use of this problem sheet then. And then just a few more things to look at here today. See, that next section at the top of page 3 is a little bit on notation. Okay, so we can write, instead of writing df dx, there is an alternative notation that's used in some books. We can just have the name of the function with the subscript of the variable that we're talking about. So this is representing here the derivative of the function f with respect to x. Okay, and similarly we can write f subscript y for df dy. From time to time, I'll use either of the forms of notation, and you will see both of them being used in various books. Obviously, the f's with a single subscript is slightly cleaner than the other notation. It's a bit more compact. But the other notation does have some advantages as well. It's easier to see partial differentiation as a process or an operator in itself. When we write things like, so you can also express the derivative like this. The partial derivative with respect to x, this is an operation which we apply to the function f. So that kind of sense is displayed by this kind of notation here. So you can see on its own, having an existence in its own right, this process of partial differentiation. And that can be a good way to think about it sometimes. Whereas with this more compact notation, f subscript x, it's a bit difficult to separate out the process of differentiation itself and see it as having its own existence and its own properties. But it is more compact, it is quicker to write, it fits on the line better than the f over the x, etc. Okay, the other thing to think about now is we've shown the definition of differentiation. We've shown a couple of examples of working out derivatives from that definition. We've introduced this principle of how to take partial derivatives of functions in general, by focusing on one variable, treating the other variables as constants, and then using the usual techniques from single variable calculus. But we haven't said a huge amount about what these partial derivatives might actually mean, what kind of interpretation they have. Okay, so we'll just spend a few moments talking about that, and this is this little section. Section 1.3, graphical interpretation, but we got a bit more, I can show a bit more of an illustration of what we mean here on the screen. Okay, so this is a computer demonstration which shows us how to think geometrically about these partial derivatives. Okay, we've got a particular function here. The function here that we're using, and I'll share this code with you afterwards. I'll put a link to this code up on Moodle probably. So you can see this yourself, and you can easily substitute here in any other function you might like. So here, this function is the sine of x times y. So f of xy is the sine of x times y. And just as for a function of a single variable, the graphical object associated with a function of a single variable is a graph. We've got the argument x on one axis, and on the vertical axis you've got f of x, and a nice continuous function gives you this nice wavy line as the graph of the function. So what's the equivalent thing to this graphical interpretation of a function when the function has two variables? Well, when the function has two variables, you've got a whole plane worth of arguments. Okay, so you've got two independent variables. So really you're talking about the information that goes into the function is points in a plane. Every point in the plane has an x-coordinate and a y-coordinate associated with it. And we can look at the third dimension using our usual Cartesian coordinates for 3 dimensions. And then we think about that the function, rather than in the single variable, the function supplies a height above the x-axis. The value of the function gives you the height above the x-axis of the point on the curve. So this is x, and this distance here is f of x. But we're going to apply that same principle here. So the function value, z, if you like, or f of xy, that's going to give us a height above some point in the plane. So if AB is in the xy plane, then this distance here is going to be f of AB, and this is going to give us a point on the graph of the function, if you like. But there's a whole 2 dimensions worth of all these points in the plane, so actually the graph is actually like a sheet, a surface. This for typical nicely varying function, you're going to have this undulating surface lying, well, above the plane if the function values are positive, or if the function values become negative, of course, it's going to go into the negative z direction beneath the plane. Okay, but I imagine a lot of you will be familiar with that idea already. And here, illustrated for us, so this is what the surface looks like for a function for that particular function, f of xy. You can spin it around and zoom in here. It looks nice. Okay, so it's this undulating surface defined by f of xy. So what have we got here? Here we've got these two curves, the green curve and the red curve. These are the two curves that are parallel to the x and y axes. See if I can remind myself which is which. So the red curve, see, this is the x-axis here, the front right. So the red curve is running parallel to the x-axis, and the green curve there is running parallel to the y-axis, which is on this side. At the moment, see, I've got these two bars here, A and B. At the moment, I'm focusing at the base point at the origin, so f of AB. So the level of the surface there is actually 0. What is sine of 0 times 0? Sine of 0 is 0. Yeah. So the level of the surface there is 0. And as you move away from the origin to other points in the plane, the function takes on various values and produces these kind of wavy features on the surface. And if we change it to just 2 other arbitrary values of A and B, so I'm changing A and B a little bit. And what I'm doing there is I'm moving the base point. And still, the red curve is parallel to the x-axis, and the green curve is parallel to the y-axis. These give us, what we're seeing there are the 2 cross-sectional curves along the surface. So the green curve and the red curve, they both lie on the surface. Now what you get if you took a knife and sliced the surface, say parallel to the x-axis, and sliced it, the knife going parallel to the x-axis and through our point AB. Then the edge of the surface that would be exposed would be this cross-sectional curve here, that red one. And if you cut it in the direction parallel to the y-axis, you would get that green curve there. Okay. Now what's going on with these partial derivatives? What meaning do they have in this picture? Well, if I take those two cross-sectional curves, you see on their own, they are just one-dimensional curves. The red curve is fixed at the y value b. Remember, the coordinates of this base point on the surface is AB. So the y value of every point on the curve, on the red curve, is equal to b, and the x value is variable. The x value is exactly equal to a when it goes through this point. When x is below a, you move this way along the curve. Or I think it's, sorry, when x is below, I think this is the negative end. When x is below a, you move that way. When x is above a, you move this way. Similarly for the green curve, but this time the y variable is varying, the x variable is fixed. So if I take out those two cross-sectional curves and just look at them on their own, so here's the one that's going parallel to the x-axis, and then the green curve going parallel to the y-axis. And I can see the base point, so that black dot in the red curve there is where that base point AB is in the red curve, and here's where it is on the green curve. Now we can see the meaning of the partial derivatives. So the partial derivative with respect to x, remember when y is treated as a constant, so y is this fixed constant b, the partial derivative of our function, which is sine of x times y with respect to x, when you evaluate it at this particular base point AB, you get 0.3. 0.3, I'm tempted to just draw a line here, I'll get in trouble. 0.3 is the slope of the tangent line to this function at this point. Okay? So the partial derivative, when you look at the cross-sectional curve through that base point, parallel to the x-axis, partial derivative with respect to x does exactly match with the idea of the meaning of the derivative just in the one variable case. That the derivative gives you the slope of the tangent line to the cross-sectional curve at that point. 0.3, slightly positive, so that agrees with this picture here that the tangent line here has got a fair positive slope. Because when you look at the y derivative, so written here is the output of the calculation, the y derivative, partial derivative with respect to y of our function f, evaluated at this particular base point, AB, is minus 0.9. It's almost minus 1. You can see here that exactly agrees here that the slope of the tangent line to this curve at this base point is it's sloping down. That's slope minus 0. So that gives you the kind of geometric meaning of partial derivatives of a function of two variables. Okay? Basic graphical object to think about, the basic geometric object defined by the function is this surface which lies above or below the xy plane accordingly as the function takes on positive or negative values. The partial derivatives tell you the rates of change of these two cross-sectional curves, which are parallel the x and y axes respectively. Okay. Any questions about that picture, or how to read, how to read that interpretation, or how to think about it, or any clarification you'd like on that? Okay. I'll put the link to this demonstration up so you can have a go at yourself or interact with it, or put in different functions at the top. And you can see the SageMath code that generated it. You can look into that as well. Okay. So let's just look at section 1.4. Yeah, so I mentioned before, during the previous example, that we were looking at these two things, which we call the first order partial derivatives. So just as in the one-dimensional case, you can take higher order derivatives. You got the first derivative, the second derivative, the third derivative. This is what you get when you iterate the process of differentiation. You take the derivative of the derivative of a function, you get the second derivative. In the same way, we can keep applying these two differentiation operators. These are the two possibilities when you apply the operator once. But if you apply it 2 times, you've got 2 different operators. So if you apply an operation twice, then there's going to be 4 possibilities. So you can do 2 of the first one, 2 of the second one, or 1 of each, but in either order. So x first, then y, or you can differentiate with respect to y first and then x. So there's 4 possibilities for what are called the second order partial derivatives. And there's nothing to stop you keeping going and looking at higher order derivatives as well. Third order derivatives, fourth order, etc. So these are the 4 what are known as the second order partial derivatives. So on the right hand side is the thing you'll understand at the moment. So this one says differentiate the function f with respect to x, and then differentiate it with respect to x again. This one does y twice. The third one there says differentiate with respect to y first and then x. And the fourth one says differentiate with respect to x first and then y. On the left-hand side is the more compact notation that we use. We use the superscript 2 to denote the fact that it's second order with d2f dx squared or d2f dx2 denotes this, differentiating with respect to x both times, similarly for y. Then we have these so-called mixed second order partial derivatives. You can call these the mixed ones because you're mixing up the y and x derivatives. So this one where you do y first and then x, this is how we write it here with the dy for y on the right and the dx for x on the left. So you're thinking of these as operations that are being composed. So you read composition symbols normally from the right. So this is the first one applied, this is the second one. So this partial derivative where you first differentiate with respect to x and then y, that would be written with dx on the right and dy on the left. You could go higher up into third order as well. And how you work these out, I mean, if you look at you just work them out using the same principle. Okay. So whichever stage of working out the derivative you are, you're focusing on one variable, you're treating the other variables as constants. You just proceed with the normal rules for differentiation that you have. Okay. Now, so this continues on with our earlier example, taking the 4 different second order derivatives of this function x squared y cubed times 2x. Because you got products of x in here, you have to apply the product rule that kind of doubles the number of terms. So if you're going to take the derivative with respect to x again, it's going to again double the number of terms probably. So the expression for d2f dx squared is kind of long, a bit awkward, but you can get to that by patiently taking the x derivative of this, which we worked out a few moments ago, or which we worked out in the last lecture, but it's back a few pages in the notes, and just differentiating it again with respect to it. But you'll have lots of applications of the product rule. To work through those carefully. Slightly easier and quicker is taking the second derivative with respect to y. Because the structure here is a function of y is much simpler, which is something times y cubed. So to differentiate that twice, what do you get when you differentiate y cubed twice? You get 6y. 3y squared once, and then 2 times 3 times y, so 6y. And the other x parts are treated as a constant, so they just hang around there and they're still there. Second order partial derivative with respect to y both times, d2f dy 2, 6x squared y times the tangent of 2x. And then the other 2 are just worked out similar. So this says first differentiate the function with respect to y, and then differentiate the result with respect to x. And this says do it the opposite way around, x first and then y. Now, when you first encounter these things, there's maybe no reason to expect that there should be any particular relationship between the 2, but you quickly notice that we get exactly the same answer. And that is true in general for most well-behaved functions, if you like. So while I said at the start that there were 4 possible second-order partial derivatives, well, really most of the time there's only going to be 3. Because thanks to this theorem, Clairaut's theorem, as long as the function is well-behaved, so in this sense what well-behaved means is, well, so as long as all the second-order partial derivatives exist, and as long as they're continuous functions, so there's no sharp features on our surface where the function makes a quick instantaneous change from one level of rate of change to a completely different one. As long as the partial derivatives are continuous, in that case, these 2 mixed second-order partial derivatives will always come to the same thing. So really, practical terms for most well-behaved functions is only 3 second-order partial derivatives. Differentiate twice with respect to x, twice with respect to y, and then the one mixed one. Okay. Now we won't be looking at the proof of this theorem, but we're going to use it all the time as an important fact. Then let's go on to the next section, 1.5. We'll do some more examples. So this example 1.4, there's nothing to stop us doing this. And we've just looked at functions of 2 variables so far, but equally well we can apply this technique and these definitions to functions of more than 2 variables. So if we look at section 1.5, example 1.4, we can apply this principle of partial differentiation to functions of any number of variables. So consider this function g of x, y, z. Now I've kept it very simple. It's just a polynomial, x squared, y 4, z cubed. Well, this is going to have 3 different first-order partial derivatives, because there's, as we understand there's 3 independent variables for the function g. So 3 first-order partial derivatives. So they are going to be dg dx, dg dy, and dg dz. So the partial derivative with respect to x, you treat the other variables as if they were constants, and you differentiate the resulting function. So the resulting function is just a constant times x squared, so it's just going to be 2 times x times whatever the constant is. The y4 and the z cubed survive, and it's just multiplied by 2 times x. Similarly, dg dy would be 4x squared y cubed z cubed, and dg dz will be 3x squared y to the power of 4z squared. Okay, so we're still using that same principle of obtaining partial derivatives. In section 1.6, we talked about the tangent plane to a surface, and I think I'll go through that at the start of my lecture next week. Sorry, at the start of the lecture next week, just as a way of wrapping up that first section. So if we look at the exercises on page 7, all of these exercises on page 7 will be open to you now. So we can definitely make use of those in this week's tutorials. And I've also got an extra question sheet, which I'm going to hand out now, which we'll make use of in this afternoon's examples class. We might get to do the first one just now.
Oh, right. Oh, this was actually really good intro. I mean,
Okay, so these questions are a bit more okay. So these questions are a bit more substantial, and they're more quoted in the context of partial differential equations. So partial differential equations are things like this: equations featuring a function that you don't know that you're trying to solve, and the operations on the function in the equations are partial differentiation. So these are the kind of things that come up all the time in engineering and physics applications, where you build a mathematical model of some engineering or physical setup. The physical laws and the physical principles generally translate into partial differential equations. Now, we're not doing the solving of them here. You've got a whole third-year course on the numerical solution of partial differential equations. I mean, in general, partial differential equations can't be solved nicely and exactly for a lot of the interesting ones that come up, and you have to resort to approximate algorithmic numerical solutions. That's the topic of the third-year course, PDEs. But what we're doing here in these questions is we're doing some verification of some solutions. So, for instance, in the first one, we have what's called Laplace's partial differential equation for an unknown function phi of x and y there. And here we're just asked to verify that this particular function, phi of xy, e to the x times sine y, is indeed a solution of it. So to do that, you're going to have to work out these two partial derivatives, second-order partial derivatives, and show that they've got the opposite sign. So when you add them together, you always get 0. Similarly, for this equation here, for the function psi, again, depending on 3 variables, and it's second order, because you've got second order partial derivatives with respect to x and y, and then the first order partial derivative with respect to t. Here we're showing that this function e to the minus t times the sum of sine x and cosine y, that that's a solution. These questions then are slightly different, and we're going to start on these in the examples class this afternoon. So question 3, we've got a function of 2 variables, and this process will become a lot more meaningful in a few lectures' time. We're going to be looking at all the occasions where the two first-order partial derivatives where they vanish. So where are the points in the plane where those two partial derivatives are both equal to 0? For that particular function, the cosine of the square of the sum of the squares of x and y. Question 4 is taking a relationship here which implicitly defines z as a function of x and y, That's the idea there. So this thing here implicitly defines the function z as a function of the two variables x and y, but not directly by a straightforward formula in x and y, but rather implicitly by this relation. And see if you can get nice expressions for the partial derivatives dz dx and dz dy from that implicit definition. The ODE in question 5 is the heat equation. So the heat equation is the equation from physics that models the distribution of heat in a region at time t. So, or more precisely, how heat moves through a medium. So if at time 0 you've got some kind of material, there's a lot of heat at one end, tracking through time how that heat passes through the material and ultimately probably evenly distributes itself across the material. But how that process happens in terms of the time, that comes from the solution to this equation here, this one-dimensional heat equation. And here we're asked to demonstrate, or we're asked to confirm, that this kind of function, e to the minus t times the sine of x, that this kind of function can be a solution of this, but there's these two unknown parameters, alpha and beta. So you're going to ask to demonstrate that this is a solution when some kind of certain relationship holds between alpha and beta. So there's something to discover here. Test out, assume that this is a solution of that, and then see if you can get the relationship between alpha and beta. And question 6 is more a kind of a geometric one. There's a diagram to go along with this of just some kind of generic triangle. The angles are A, B, C here. And little a, little b, and little c are the lengths of the opposite sides. So little a, little b, and little c are opposite their angle partner names, A, B, and C. And here what we're imagining is we're keeping the length of these two sides fixed. But imagine opening and contracting this angle A. So keeping the length of B and the length of C fixed, imagine those as two sticks, but varying the angle A. Now that's going to induce some kind of, we're imagining varying the length of side A. So keeping it a triangle, but opening up B and C by expanding or contracting the length of side A, can we determine what the rate of change of the angle, capital A, is as the side length, little a, varies? So obviously as you shrink side length A, the angle A is going to shrink. As you expand side length A of the triangle, the angle, capital A, is going to increase as well. Well, what's the relationship? Find the rate of change of the angle A as the side length has varied. So really what we're looking for is d capital A, d little a. How can we get that? And we get it via implicit differentiation and this relationship from the triangle, which is of course the cosine formula, which relates the side lengths A, B, and C and this angle here. So what's required to solve all these equations is just careful application of the principle of partial differentiation, which we've outlined a few pages ago. This principle here, in the bold, on page 2. Combining that with all the theory about single variable differentiation that we had from last year, should be able to solve all those problems. Okay. So we'll pick these up this evening for the kind of examples workshop class this evening. Okay. Okay, good. If you came in late and you didn't sign the signature sheet, it's up here. Please do.